Hello, everybody. I hope everybody's doing okay, and want to get you guys ready for the exam that's next week. That will be on the 6th, May 6th, Wednesday at the regular class time. You'll have an hour, so make sure you do not miss this one. All right, and important to be there, be able to take that in that regular class time slot. So let's go over the study guide. I want to get you guys ready for it. And so the first thing for this exam is we talk about the mass loss of stars. Remember, stars lose about 50 to 90% of their mass as they die. Remember, they can either die in a planetary nebula for a giant star or a supernova of a supergiant. So they lose a lot of mass. Remember, what's left over is the core. So they lose about 50 to 90% of their mass, and we call that mass loss. Now, explain how stars undergo mass loss. What you do for that, or just to understand, is that either stars go through the planetary nebula stage for the lower mass stars, these giant stars, when they swell up, or supergiants go supernova. So that's how they undergo a lot of mass loss. There's other ways stars lose mass, but mainly a planetary nebula or a supernova. And now, stellar core is left over after the death of the star and the mass ranges. So it's really good to know that a white dwarf is a stellar core, degenerate matter, super dense matter. Its mass is anywhere from 0.3 to 1.4 solar masses. A neutron star is the mass of this stellar core. Again, neutron star from a supergiant as opposed to a white dwarf from a giant star. So a neutron star's mass range, 1.4 to 2.2 solar masses. Neutron star, 1.4 to 2.2 solar masses. And anything over 2.2 solar masses, that core is going to have enough mass to have enough gravity that it will collapse down and become a black hole. So a black hole over, a stellar mass black hole over 2.2 solar masses. Remember the Chandrasekhar limit, the 1.4 solar masses. That sub-Ramanujan Chandrasekhar figured out that was the upper mass limit for a white dwarf. Degenerate matter, super dense material, white dwarf material, neutron star material, a black hole singularity, very, very dense material. It's called degenerate matter. White dwarfs, no properties of, it's good to know the properties of white dwarfs. Like, again, the mass range, approximate size. What keeps a white dwarf from collapsing due to gravity? What else? An example of a white dwarf we talked about. So go take a look at that white dwarf information. Neutron stars. It's good to know what a neutron star is. Remember, it's something even more dense than a white dwarf. It's very small. It's even more, I mean, the density is, well, we said expletive dense compared to a white dwarf. Remember these pulsars, too, were these rotating neutron stars beaming EMR along their magnetic field axis. Remember Jocelyn Bell? Good to look her up, what we talked about Jocelyn Bell, very important. What a black hole is. A lot of this test is going to be black holes. It's good to define a black hole. It's good to define like the event horizon of a black hole. What are the gravitational radius? Identify the forces keeping gravity from collapsing these stellar cores. Remember, for a white dwarf, electron pressure. Neutron star, neutron pressure, the strong nuclear force, or neutron pressure, the strongest force we know. And if it's a core that's over 2.2 solar masses, remember, no known force stops the collapse, and that's why it collapses into a singularity and becomes a black hole. So explain how a stellar core becomes a black hole. Well, if you have over 2.2 solar masses, gravity is so strong, there's no force that can stop this collapse. And if it collapses beyond its own event horizon, you have created a black hole. Be able to define what escape velocity is. Know what the escape velocity from a black hole is. Know what the escape velocity from the event horizon of a black hole is. Know what the escape velocity is if you're just outside the black hole. What would the escape velocity be relative to the speed of light? So it's good to know what escape velocity is. Like the escape velocity from the Earth, remember, it's much less than the speed of light. That's how we can send things off of Earth. So the escape velocity of pretty much anything is less than the speed of light, except when you're talking about like a black hole. And then we're getting to regions where the escape velocity is greater than the speed of light, and that's when you have a black hole. Schwarzschild radius, or gravitational radius. Just no gravitational radius. The radius of a black hole. The event horizon. The theoretical edge or boundary of a black hole. Einstein and relativity. Talk about Einstein, or be able to talk about Einstein and the general and special relativity. What general relativity is. Remember, mass warping space and time. What special relativity is. What a dimension is. What Roy Kerr figured out. What the twin paradox is. Good to know. That's special relativity. What problems might you encounter if you get too close to a black hole? We talked about a couple of things. We talked about sending Joe in there and having Joe getting the tidal force is so great that Joe gets spaghettified, gets stretched into a string of atoms. So anything for a lot of black holes, well, maybe not everyone, but everything's going to be spaghettified, and nothing will stay intact if you get close to one, too close to one. And also, we talk about the time. If you watch someone going into a black hole, they would seem to get slower and slower, and their clock would appear to be slower and slower, and you would never see anything from your point of view in less warp space-time fall into a black hole. Right at the event horizon, it's like almost infinitely warp space-time. So everything should be that ever went into a black hole, you should see an image of right at the event horizon. Be able to define a tide or a tidal force and discuss why it occurs. Types of black holes. Now, it's good to know a little bit about this. It's good to know the mass ranges for each of these types. And also the tidal forces. Remember, the smaller the black hole, the stronger the tidal force at the event horizon, and the bigger the black hole, the weaker. So this is most of the test, what we've already talked about. I would say that 75, 80, even a little more percent of the test. And then we get into this, a little bit more here. Not that much more. The interstellar medium. There might only be one or two questions about the interstellar medium. We have dust and gas. With dust, we have dark nebulae. We have reflection nebulae. So take a look at those. Think of an example for each that we talked about. Gas, we have the H1 cool hydrogen regions and the H2 regions. The H2 regions are emission nebulae, planetary nebulae, and supernova remnants. So altogether, with this and this, maybe 3 questions, not much at all on the test. Star clusters, open and globular. I only put, I think, 1 question about open and globular clusters there. But then we get into the galaxy and our galaxy. So it's good to know astronomers like Galileo, Herschel, Shapley. We talked about them a little bit. It's good to know the Hubble types of galaxies, spirals, barred spirals, ellipticals, irregulars, and lenticulars. Know which ones have a lot of dust and gas. Know which ones have not much dust and gas. Know which ones have star formation. Know which ones might be the most common. Know which ones may be the most commonly observed. Know which one might be the biggest ever seen. Know which type maybe the Milky Way is. So there might be a few galaxy questions on there. Don't worry about active galactic nuclei. Been covered for this test. You can cross that off. You can cross off clusters and superclusters of galaxies. And this stuff, cosmology, all of this is not going to be on exam 4. It's just going to be on exam 3. So, no, cross that, not on exam 3. We already had exam 3. So it will not be on exam 4. It'll be on the final. So all of this cosmology, starting with cosmology here, that material, along with everything else in the class we've talked about on the test, will be on the final. Again, the final is going to be regular time of the final. We have that written down. And you will, it'll be 40 questions, mostly stuff we've already talked about, very similar, not the exact same questions, but very similar questions for the final. So there it is. There is the study guide for exam 4. Again, that will be next week on May 6th, and it will be the regular class time. So don't miss it. And that is it. Email me if you have any questions. Take care.